right, well, thank you very much for organizing, to the organizers. It's really exciting to be here in Tokyo. It's my first trip to Japan, and also the first time I've given a live talk in 2.5 years. So I'm trying to remember what I did with my hands and all kinds of other things back before the pandemic, but we'll figure that out together. So with a short 20-minute time frame, let me just jump right in. I don't need to introduce myself anymore. So at a quantum computing conference, it may be that some people in the audience aren't familiar with the breadth and the depth of the NVIDIA accelerated computing platform. So I do want to take a minute here to just give a brief introduction. So with the invention of the GPU, NVIDIA propelled the development of the PC gaming market, reinvented computer graphics, and ignited the era of modern AI. Today, NVIDIA is a full accelerated computing company. We start with CPUs, GPUs, DPUs, and then build the software that create data center scale solutions. Before we jump into defining the quantum accelerated computing supercomputing platform, I think it's worth taking a minute to just review what are the major workloads of supercomputing today, the modern supercomputer. Simulation is the foundation remains the foundation of supercomputing. Over 20 years ago, scientific developers started using GPUs to get to accelerate their workloads and get performant and solve problems that they weren't able to solve before. With the invention of CUDA in 2007, NVIDIA ushered in a revolution in accessibility of a disruptive compute technology, the GPU. Today, though, the modern supercomputer has to consider 4 additional workloads: HPC plus AI, digital twins, scientific edge, and of course, quantum computing. Digging in on quantum computing. The first thing I want to do is take a look back at what we've done over the last 10 years in this community, because it's really important and starts to frame up what kinds of problems we should solve today and what problems we need to solve as we move forwards. The progress that the quantum computing industry has made is really impressive. A decade ago, we were looking at 1 to 2 qubits in academic settings. Today, we have systems with 100, 200 qubits that are available publicly through the cloud. However, we have a very long ways to go. Generally, the industry agrees that quantum advantage for a broad range of applications will happen in the era of fault-tolerant computing, consisting of millions of qubits that are error-corrected down to thousands of logical qubits. But there's a tremendous amount of energy and investment in order to get us there. Worldwide, we count 22 government initiatives in quantum computing, over 2,100 research papers, 250 quantum computing startups, and growing. And if we survey the major corporations of the world, we see that over 70% of companies have some kind of quantum initiative. As we think about going from where we are today with hundreds of qubits in the cloud and towards that fault-tolerant quantum computing future, one of the most important tools that we have to push forwards is quantum circuit simulation. And so as NVIDIA started to look at quantum computing and decide what should we do to help move this industry forwards, we announced Q-Quantum about 1.5 years ago. And what Q-Quantum does is it plugs into the major quantum circuit simulation frameworks that we all know, they're household names today, and provides a scale and performance that unlocks the ability to solve problems that just weren't possible before. We're really excited about the broad adoption that Q-Quantum has had in the industry, from the quantum computing frameworks like Cirq, Qiskit, PennyLane, and many others, but also with industrial end users, with supercomputing centers, and with the whole quantum computing ecosystem, leveraging Q-Quantum and quantum circuit simulation to solve harder and harder problems and help push the industry forwards. With a relatively brief time here, I can't talk about all the success stories of our partners with Q-Quantum, but I do want to highlight a few recent examples. Pascal has been looking at integrating Q-Quantum to do faster quantum algorithm development for physics ML, seeing 100 times faster time to solution with 24 times more circuit depth. Recently, we announced a partnership with Xanadu and AWS with integration of Q-Quantum into PennyLane and then availability of that through the AWS bracket service. There we saw 900 times faster time to solution and 3.5 times lower costs. Zapata is integrating Q-Quantum into their Orchestra platform, and seeing 100 times faster time to solution, and as well as the ability to simulate 1.5 times more qubits. As we move on to other areas and think about what else do we need to do to push the quantum computing industry forward, we want to take a minute and acknowledge that when we see quantum advantage, these applications will not be running exclusively on a quantum resource. They'll be hybrid applications. And by a hybrid application, I mean an application which is leveraging the best of a classical resource for the algorithms which make sense, and the best of a quantum computing resource for the algorithms that make sense as well. But taking a look today at the application ecosystem and what it would need in order to move forward, we notice that there really isn't a performance software stack, and that the ways in which we program quantum computers today is not accessible to the traditional domain scientist, to the non-quantum physicist. NVIDIA has actually quite a bit of history and experience in this area. If we go back to 2006, right before the announcement of CUDA, there were scientific developers who were leveraging GPUs to accelerate their work. However, there were very few. And the reason for that is that they had to program in graphics and shader APIs, or the equivalent of GPU assembly. And so from that perspective, the announcement of CUDA in 2007 ushered in a revolution in developer accessibility for a disruptive compute technology, the GPU. And that really springboards us into our new announcement here today, and that is I'm delighted to announce the NVIDIA Quantum Optimized Device Architecture, or CODA. So CODA is a platform for hybrid quantum classical computing. Critically, it supports any kind of QPU, emulated or physical. It includes a compiler for hybrid systems, so you can get the best of classical resources and quantum resources working together. It is open and interoperable with today's applications. And what I mean by that is it enables a scientist who has an application they're already running on the most powerful computers of today. It enables them to seamlessly integrate quantum computing into their application where it makes sense with the algorithms that they're developing. To start, we have a single source C++ programming model, as well as Python wrappers around that. And over the next few slides, I'm going to dig into a couple of the features that are most important about CODA. This is not going to be a deep technical talk. However, if you're interested in the technical details of CODA, Bryce Adelstein-Laubach, who's one of the programming model architects developing CODA, will be giving a talk tomorrow, and I would encourage everyone to come and listen for more details. I do want to take a brief look at code, even though I'm not going to be giving a very technical talk, and there'll be a little bit more code on ensuing slides. I think that if you are developing quantum algorithms today, you'll certainly see what's going on here. This is an example of a variational quantum eigensolver that's written in CODA. However, at a high level, what I want people to notice is that this will look very familiar to a scientific developer who's developing an application in C++ today. And that's one of the critical features of CODA, is to wildly increase the accessibility of quantum computing to scientific developers who don't have a quantum computing background. Now, as an accelerated computing company, I certainly need to talk about performance as well. CODA is designed from the ground up to give incredible performance on hybrid systems, whether they're emulated or using true physical quantum processors. In this example, I'm showing a comparison between CODA running on a single A100 GPU against a leading Pythonic framework also running on a single A100 GPU. And the reason for doing a GPU to GPU comparison is that we want to isolate the benefit of CODA on the same hardware. So for a variational quantum eigensolver here, we can see that at 20 qubits, we're up to 287 times faster than the leading framework today. This is really an incredible boost in performance that will allow people to solve much larger problems and iterate faster in their algorithm design as they prepare and develop quantum accelerated applications. One of the features of CODA that I want to emphasize is that it's built to interoperate with the programming models and the ways in which applications are developed today. CODA is interoperable with standard language parallelism in C++. It's interoperable with OpenMP, it's interoperable with OpenACC, it's interoperable with CUDA, and it's interoperable with a whole suite of libraries that are used in today's scientific computing application development. In this case here, what we're looking at is the kite algorithm, or quantum imaginary time evolution, just the inner loop. And what happens here is we have to compute expectation values, something that we think a QPU will be very good at, and we implement that with CODA. That then feeds into a dense linear solve. GPUs are very good at dense linear solves. And so we can use the cuSolver library, which is a library developed by NVIDIA for giving high performance on NVIDIA GPUs. The results of that linear solve are fed back into the Coda code at the top, where we compute expectation values again. This algorithm is really intrinsically hybrid and iterative. And so it's a great way to show off the way that we can interoperate between GPU code and QPU code using Coda. Together, oh, sorry, wrong slide. So one of the other things that Coda allows us to do is to experiment with hybrid quantum deployments, which are not practical in the near term. One example here is that we can explore what it would be like to program multiple QPUs. So here we're looking at running a hydrogen chain VQE iteration, where we're going up to four simulated QPUs, each being programmed on a single A100 GPU. And we actually see near perfect strong scaling as we go from 1 to 4. Now, clearly, this would not be a practical simulation to run on quantum hardware today, but Coda includes underlying abstractions which enable the developer to experiment with a broad range of types of quantum deployments. One of the most important things about the Coda announcement is really about the partnerships. So when we were on the cuQuantum slide earlier, there were a whole range of logos, and that really is because one of NVIDIA's core strategies in quantum computing is to be a partner to the entire ecosystem. That's true as well with Coda. And in this case, we're really excited to announce we have 5 quantum hardware partners in the announcement who are working with us to support Coda on their actual physical QPUs. That includes IQM, Pascal, Quantinuum, Quantum Brilliance, and Xanadu. Additionally, leading quantum software companies, QCware and Zapata, are collaborating with us to use Coda with end users who are building the hybrid quantum classical applications of the future. And supercomputing centers are working with us to test and deploy Coda for thousands of scientific computing developers around the world, including ULISH, NERSC, and Oak Ridge National Laboratories. Together, the DGX Quantum Appliance and the Coda create a powerful platform for quantum computing research and hybrid development. With the DGX Quantum Appliance, researchers can develop and test new and improved quantum algorithms, accelerating their timeline to quantum advantage. With Coda, they can take today's most important application codes and seamlessly run them on the leading classical hardware, emulated quantum hardware, and actual quantum hardware, or any combination thereof. When integrated with our partners' QPUs, this platform will define the world's first quantum accelerated supercomputers. Quantum computing holds incredible promise for solving some of our most challenging and important problems, but still has a long way to go to realize its potential. Today, we are announcing a platform that will help us get there. By providing a programming model that is interoperable with today's most important scientific computing applications, we're opening out the programming of quantum computers to a massive new developer base of domain scientists and researchers. By building a software toolchain that's optimized for performant execution of hybrid code, we are removing bottlenecks on the path to quantum advantage. And by partnering across the stack, from QPU builders to algorithm developers to end users and research institutions, we're ensuring that we're bringing the best tools to bear to help solve these problems and enabling the entire quantum community to contribute to that effort. And that's all I have today.